Okay, so let's solve the problems of the second worksheet for exam 2. And the first problem, we're given a function f of xy ln of x squared plus xy cubed minus 5. And we want to find the directional derivative in the direction of the vector square root of 3 over 2 comma negative 1/2 for the function f at the point 2, 1. So it's enough to find the dot product of the gradient at the given point with the direction vector. And how do we find the gradient? We need to find the partial derivatives. So we will have f sub x is 1 over x squared plus xy cubed minus 5 times the derivative of the interior with respect to x, which is 2x plus y cubed. And this means that f sub x at 2, 1 is going to be 1 over 1 times 2 times 2, which is 4 plus 1 cubed. This is 5. And f sub y will be 1 over x squared plus xy cubed minus 5 times x times 3y squared. Okay, and f sub y at the point 2, 1 is going to be 1 over 1 times 2 times 3 times 1 squared, which is 6. So this tells you that the gradient is going to be 5, 6. And if you take the dot product of the gradient with a vector, the direction vector in the direction of the sought for partial derivative, it's going to give you 5 square root of 3 minus 6 divided by 2. So we multiply 5 times square root of 3 over 2, 6 times negative 1 over 2, and we add them up. And that's what we find. And that's our first problem. Let's go to our second problem. We consider the function g of xy to be xy over x plus y. And we want to find the unit vector pointing to the direction of fastest increase for g at the point 2 comma negative 1. Okay, so from our theory, we know that the direction of fast increase is the direction of the gradient. So what we need to do is find the gradient. This is not necessarily going to be a unit vector, and we need to normalize it. Okay, so that's what we're looking for. So it's enough to find this. So again, in order to find the gradient, let's find the partial derivative. So g sub x is going to be the derivative of the numerator, so that's y, times the denominator, minus the numerator times the derivative of the denominator, which is going to give you x plus y squared. So this will be yx minus xy, that's 0, so that would give you y squared over x plus y squared, implying that g sub x at 2 comma negative 1 is going to be 1. Now, a nice little remark here is that since everything is symmetrical with respect to x, y, when you try to find the derivative with respect to y, it should be the same formula pretty much with y and x change. So this will be x squared over x plus y squared, which is of course what you would find if you did again the quotient rule. And this would mean that g sub y of 2 comma negative 1 is equal to 4. Okay, so our gradient is the vector 1, 4. And if we normalize it, its magnitude is square root of 1 square plus 4 square, meaning 1 square, square root of 17. So what we're looking for is this vector. Okay, the normalization of 1, 4, and that's it. Okay, let's go to our third problem. In the third problem, we have the function f of x, y, z equal to x cubed plus 3y squared plus 5z. So find an equation for the tangent plane to the surface. So that will be a level surface for the function that we just gave, corresponding to the value 1 at the point 2, negative 1, negative 2. Okay, so what do we do here? What we want to do is, sorry about this, is take into consideration the fact that the gradient at the point 2, negative 1, negative 2 is going to be perpendicular to the surface, meaning, so perpendicular to the level surface at 2, negative 1, negative 2. Hence, it's, so therefore, sorry, Zoom is playing games with me. So hence, normal to the tangent plane. Okay, so what is the gradient? So the gradient, these partial derivatives are so simple, I'm not sure we need to compute them in a painstaking way. So the derivative of x cubed is 3x squared, plug in 2, that will give you 12. Derivative with respect to y will be 6y, plug in negative 1, that will give you negative 6. Derivative with respect to z is 5, that's a constant. Okay, so again, just to make sure that, so f sub x is 3x squared, which means that f sub x at 2, negative 1, negative 2 is 12. F sub y is 6y, which means that f sub y at 2, negative 1, negative 2 is negative 6, and f sub z is simply 5, which means that f sub z at 2, negative 1, negative 2 is equal to 5. And we have a point. We have the normal vector. How do we find the equation of the plane? We know that it's going to be 12 times x minus 2, minus 6 times y plus 1, plus 5 times z plus 2. And of course, don't forget to put equal to 0 since we're looking for an equation. Okay, so what we just used is the fact that if you have a plane that contains the point x naught, y naught, z naught, and a perpendicular vector to that plane is given by a, b, c, a normal vector as we say, then the equation of the plane is a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. Okay, this just as a reminder. Let's go to problem 4 now. So we're given the function f of x, y equal to 8x cubed plus 6xy minus y cubed. And we would like to find and classify the critical points of f. So this is a problem on the second derivative test. Find and classify the critical points of f of xy. And to do this, we first need to find the critical points. What are the critical points? Points at which the derivative is, both partial derivatives are equal to 0. So the partial with respect to x is going to be 24x squared plus 6y. The partial with respect to y is going to be 6x minus 3y squared. Set them equal to 0. Let's start with the first one. If you divide through by 6, you get y is equal to negative 4x squared, right? Once you know that y is equal to negative 4x squared, you plug it into the second equation, and that will give you 6x minus 3 times negative 4x squared is equal to 0, which will give you 6x minus, plus actually, oh sorry, minus 48x to the fourth is equal to 0. Factor out 6x, that will give you 1 minus 8x to the third is equal to 0, which means that x is 0, or 1 is equal to 8x cubed, which means that x cubed is equal to 1/8, which means that x is equal to 1 over cubed root of 8, also known as 1/2. So if x is 0, go to this equation, and that will give you y 0. So one critical point is 0, 0. If x is equal to 0, then y, I'm sorry, we already did that, right? So what we want to do is x equals to 1/2, then y is going to be negative 1. So we get the point 1/2 comma negative 1. Okay. And now we want to apply the second derivative test. So we find the second partial derivative. So f sub xx is going to be 48x, and fxy is going to be 6, constant function. Fyy is going to be minus 6y. So start with 0, 0, and compute the determinant fxx at 0, 0, fxy at 0, 0, fxy at 0, 0, fyy at 0, 0. This determinant really tells us whether we have the same behavior for the function along all directions. When I say behavior, I mean local mean, local max. If it's the same, then it's going to be a local minimum for the function. If it's not, then it's not going to be a local extremum. In any case, what we get here is 0, 0, 6, and 6. This is negative 36 is less than 0, and this is a saddle point. Saddles have the same shape as Pringles, sometimes I like to call this a Pringle point. That's a term coined by Terence Tao. So it's funny. It's, well, you could misconstrue it as a commercial for Pringles, but in any case, Pringles are tasty. So I can assure you I'm not getting a kickback from, or mathematicians do not get a kickback from the Pringle company. But in any case, let's do the next one. And again, same story. We have to compute the partial derivatives, the second order partial derivatives, and put them in this determinant. Let's see what we get this time. So we will have 24 and 6 and 6 here. And FYY will be simply 6, right? So you will have 24 times 6 minus 6 squared. That's definitely, I mean, that's if you factor out 6, that's 24 minus 6 times 6, right? Also known as 18 times 6. Definitely a positive number, which tells us that we have the same behavior along all directions, and we need to sample one direction. So we take f sub x x, that at the point 1 have -1, which is equal to 24. This is greater than 0. I remind you that second derivative being greater than 0 tells you you have a concave up function. That's the shape of a smile, and that gives you a local minimum. And this completes this particular problem. And now let's turn to integration. So let's go to problem 5. It's a very, very simple double integral. It's the integral of x squared plus xy dA 0 to 0, 1. This can be automatically written as a double iterated integral. So you want to start with 0 to dx, and then 0, 1 dy. You integrate from the interior to the exterior, and you have x squared plus xy. So let's find the antiderivative first with respect to x. And this will be x cubed over 3 plus x squared over 2 times y from 0 to 2. And then you have to go 0 to 1 dy. So how much is this? You have 8/3, and you have 4 over 2, that's 2 y from 0 to 1 dy. And this is going to be 8/3 y plus y squared from 0 to 1, also known. I hope I didn't do any numerical mistake. If I did, please correct it. 8/3 plus 1, and it's the same thing as 11/3, and that's it. Let's go to problem number 6, where we have a very interesting situation here. We would like to compute the integral of 0 to 2 e to the x squared dx, and then dy, and that should go from 0 to 4. Okay, so we want to compute this integral. And the problem is that if we try to, this is a double iterated integral, if we try to do the inner integration, then unfortunately, we will realize that it simply doesn't work. Okay, because yes, e to the x squared has a perfectly fine antiderivative. The problem is that it's not expressible using functions that we know, so we get stuck right there. Not every function has a formula in terms of our usual functions. So that's a problem. And pretty much what we do here is we ask ourselves, what if whoever wrote this double iterated integral didn't choose the best possible order for integration, meaning they chose dx first, dy second, so horizontal integration first, vertical afterwards. How about if we try to do it the other way around? In order to do that, we have to first go through the double integral. If you like, we need to sketch the domain. And in such a situation, we have a left boundary that is, I'm sorry, this was a y right here. A left boundary, which is x equals y, and the right boundary, which is x equals 2. Actually, in this problem, I'm sorry, this was not a 4 as I was looking. This said 2. Sorry about this. So if we try to sketch those things, so the left boundary is really the bisector of the first quadrant, and the right boundary is this vertical line. And we know precisely that we go from 0 to 2 vertically, which means that our domain of integration is exactly this triangle. So I repeat, the left boundary is this line, the right boundary is that line, and we know that integration takes place from 0 vertically all the way to 2, which means that we have exactly this triangle. And now we can ask ourselves, how can we do this the other way around? So start with dy. If you want to start with dy, then you have a lower boundary and an upper boundary. The lower boundary is simply, let me try to draw it here, is simply the x-axis, also known as y equals 0. And the upper boundary is going to be just the bisector, right? So that means that we will go from y equals 0 to y equals x. And then the horizontal range of all these vertical integrations is going to be from 0 to 2. And the integrand is simply e to the x squared. I'm sorry, this is problem 7. Okay, sorry about this. Okay, now, what has changed here? What has changed is the fact that now you're doing the integration with respect to y. And with respect to y, this function is constant, which means it has the easiest derivative that we can possibly have here. It's simply y times the constant number. Yeah. And you want to go from 0 to x, and this will be from 0 to 2 dx. So this will give you the integral from 0 to 2 of x e to the x squared. Here, you might want to say that you go from y equals 0 to y equals x. I mean, we know that we did the integration with respect to y, so that's superfluous, but, you know, it's a good idea to be as clear as possible. And now this integral is not a problem anymore because we can do a substitution. U is equal to x squared, du is equal to 2x dx, and x dx is equal to 1/2 du. And that would give us the integral of 1/2 e to the u du. And now you have to be careful because you have to apply the substitution to the endpoints. So you have to go from 0 squared to 2 squared, meaning this is going to be 1/2 times the integral from 0 to 4 of e to the u du, which is 1/2, and the derivative is the u, 0 to 4, which is 1/2 e to the 4 minus e to the 0. And of course, I remind you that e to the 0 is the same thing as 1. And that's our final answer. Okay. And let's solve one more problem, problem number 8. And here what we want to do is use integration in polar coordinates in order to compute the double integral of xy dA over the domain D, where D is, let's see if we can draw this. It's the part of the disk of radius 2 centered at the origin. So let's sketch that disk of radius 2, for which it says, or the part of it lying in the quadrant for where x is less than 0 and y is greater than 0. So x is less than 0 and y is greater than 0 is right here. Okay. So that's what we usually call the second quadrant. And I also want you to understand that we could have said the x less than or equal to 0 and y greater than or equal to 0. It would have been exactly the same computation because you're including or excluding, if you like, parts that have volume 0. So what do we do? First of all, describe the domain in terms of polar coordinates. So this is r theta, so that r is between 0 and 2, and theta is between pi over 2 and pi. Again, it doesn't really matter whether you put inequalities, strict inequalities, or just weak inequalities with also the equality sign. The integral that you will need to compute will be from 0 to 2 matching with dr, and pi over 2 to pi that is matched with theta. So that takes care of the domain, which is usually the most important step. How about the integrand? I remind you that in polar coordinates, we have that x is equal to r cosine theta and y is equal to r sine theta. So this will give us r cosine theta times r sine theta, and that takes care of the integrand. And there's one last step to not forget the Jacobian, which is r. So here we will have the integral from pi over 2 to pi 0 to 2 r cubed cosine theta d theta, sine theta d theta. Sorry, dr d theta. And let's do the integration first with respect to r. That will give us r to the 4 over 4. The quantities that have theta in it are constant. And we need to go from 0 to 2. And then the integration will take place from pi over 2 to pi d theta. And this will be 16 over 4 cosine theta sine theta. And the integral from pi over 2 to pi d theta. Now, here we can do a change, a substitution. U is equal to sine theta. Du is equal to cosine theta d theta. So this will give us 4 outside. And we will have, so cosine theta d theta is r du. and sine theta will be our u. And now you have to be careful. You don't write here pi over 2 to pi. You take these endpoints and you plug them into your substitution. So you have to go from sine of pi over 2, which is 1, all the way to sine of pi, which is 0. And this will give you, if you want to turn it into a -4 of the integral from 0 to 1 u du, which is going to be -4 times u squared over 2 from 0 to 1. That's going to give you -4 times 1/2, also known as -2. Sometimes people panic at this point and they say, oh, we found negative volume is that can be right and so on. But, you know, look at your initial function. It's x, y, and the domain of definition is the second quadrant. X is negative, y is positive, so their product is negative, which means that the whole region whose area, whose volume you're computing is under the xy plane. Remember that the integral, the double integral, represents signed volume, and parts that are below the xy plane are counted as negative. So it makes perfect sense that we found a negative number. It would have been actually a problem had we found a positive number. So we're all good, and that completes our problem and our set of problems for that matter. Thanks for watching.